right, so welcome again, everyone. It's already 10 past 3, so it's time to start our next lecture today, which will be given by Nis Meinert, again on a series in the series of modern C++, but introducing the new topic of demystifying value categories. So Nis, whenever you're ready, please share the slides and go ahead. Thank you.
Okay, thanks. So I think I already started to share the slides.
No.
You don't see it? Okay, wait, give me a second. So now you should see it.
Yes, we do. Thank you.
Okay.
And we
great.
can see you well.
Great, wonderful. So first of all, I also posted the link to my slides to the chat, and also for the MetaMost page. So same procedure as in the previous talks. Please interrupt me at any given time and using the Zoom chat, MetaMost, or just by raising your voice. Okay, so this talk is about demystifying the value categories in C++, which is a topic that I skipped for quite long, and I think it is the very same for most of you. Can you use the full screen? It's a bit difficult for me. I hope it will suffice as doing as this. I hope. Let me give you a brief introduction into this. So first of all, C++ has the big advantage that you can reason about value categories, because this really opens the door to find unnecessary copies that you do, and depending on your problem and the data structures that you're copying, this can be a huge performance improvement if you can avoid copying large arrays, for example. But as many things in C++, in case you're not really interested in really going deep into your source code and try to find these copy constructors, then this talk might not be the right talk for you, and maybe you should be down the hole in the Python room, as Scott Meyer said once. So, but if you're interested in, please pay attention. So I divided this talk into two parts. Today is the first part where I will briefly introduce you to references again. So it's really about understanding what is a reference. Then we can talk about value categories, perfect forwarding. And then we have to do a small session about reading assembly, because this will help us to understand implicit costs of const references. And we will also need this as a background in the second part of this talk, where we want to understand RVO, so return value optimization. Okay, so let's dive in with part 1, understanding references. So to wake you all up, I've created a small poll. So your task is to guess the return value, the returns, or the outputs of the Python program on the left and the C++ program on the right. So what should be very simple. The idea is that we implement a swap function. This is quite easy in Python to do, because in Python everything is passed by reference, right? And so we can simply swap those two things. And if we want to do the same in C++, well, it's a bit more code, but technically the same thing. We receive references and then we swap those. So I now start the polling, and you should tell me the output of this program. Okay, you're again quite active. It's very nice to see from me. Okay, Okay, so already 80 of you have voted. So I give you a few more seconds. Maybe we can reach 100. Okay, great. So let me end the polling here and share the results. Okay, so most of you think that the swapping does work and the return values should be 2, 1 and 2, 1. So we basically stop it. Let me stop it here. Okay. So the return value for the Python program is 1, 2, and for the C++ program 2, 2. So ouch, what's going on here? Well, it's not a talk about Python, but so let me be very brief about this. Actually, Python does not pass arguments by reference. For most of the time, it seems to be like this, but technically it's passing by assignment. But as I said, it's not a talk about Python, so let's skip this part. But what is going on with the C++ program? So some of you were right to see that we are passing references, so this is fine. But what's going on in line 8 is that we are just creating an alias for, in this case, our reference A. Then we do an assignment, so we override the reference that passed an A with B. And since TMP is just an alias for A, then assigning B to the reference to A, which is now B, is basically the same as saying B equals B. So this is the reason why we see 2, 2 as the output. Okay, so how do we fix it? Well, one easy approach is just to remove the reference here. So now we are doing a copy and save this into TMP, and then when we run this program, we indeed see that our swapping works. Now the return is 2, 1. Okay. So let us investigate a bit more what is going on here. So so this is the first this very same program I show you on the first slide, but this time I enriched the constructors of S a bit so that we can see what is actually going on. So when the constructor is called, then we will see printed A. If the copy constructor is called, we should see B. And when the assignment operator is called, we should see the letter C. So this is the same program as before. So we so where the swapping still does not work. So when I print the values down here, I will see 2, 2. But before this, I will actually see what is happening. So we see that we create two objects with this this constructor. This is fine. This is what we expect. This is basically this line down here. But then we do the swapping, and during our swapping, we emit 2 times the letter C, because we do two assignments here. Okay, that's already not quite nice, because actually we just want to swap references. There shouldn't be any assignment going on here, right? Well, so let's keep this in mind and go to the next example where I removed the reference here. So this is the example where the swapping actually works. And your task is now to tell me the output of this program. Let's start the poll again. We don't. And again, if you have any questions, please just ask me by using your voice or writing those to the chat. This is a perfect time now to answer, or first to read the questions for me, and then eventually to answer them. So still very active, great to see. So let me end the polling here. And most of you got the correct answer. So let me end this. So the output is actually AAB, CC, and to one is not a surprise. AA is also not a surprise. And in principle, we already covered the reason why we see B and CC. The main thing I want to convey here is that this is actually absolutely not acceptable. We just want to swap two references, and now we are within this swapping process. We are invoking a copy constructor and two assignments. This is super expensive. At least it could be. So maybe references are not the right tool here. So let's go to use pointers instead. So basically the reference are gone now, and we use references here. And this of course also means that we have to we use pointers here, and this of course also means that we have to pass the address of object A and object B here. So what do you think? What is the output of this program now? And I promise there will not be so many polls left. Oh, okay. So Sebastian asked me, once the poll is over, do you share the results? I thought that I do, but I will check this time. But the last poll was the result of the last poll was basically the right answer for the majority of the people. Okay, let me end the polling here. And this time share the results, and now you should see it. Do you see it? Yes, wonderful. Okay. So maybe this was a mistake from my side the first time. So let me end this here. See them before as well. Okay, great. So what is the output? AA12. So the swapping didn't work, and so some of you already found out why. Well, what is actually going on? We are just changing inside the swap function where this pointer points to. So the pointer is in some sense copied by value here, not by reference. And so we just change it here. So let's see how we can avoid this. So, and at the first place, well, let us split this a bit here down in the main program. We're not now not just passing a, but variable a pointer, which basically is the pointer to a, but we want to swap these in the next instance. So now the result should be the same as before, and you will see it is. So no swapping here. But now we can do this crazy shit. We can say pointer to S copied by reference. And I spare the poll here. This will now actually work. Now we pass a pointer by reference, and then we can swap it. And this is really what we want to do now. So now the result is AA to 1. So no unnecessary copy or assignment is going on, and we really swapped the pointers. But we had to pay a price. So we now had to split this line into two lines. Well, let's see if we can improve on this point a bit. So sorry, my phone just went off, and I used this to watch the poll. Give me a second. Okay. Now I see it again. Great. Well, then suddenly we get a compile time error. So now the compile time error reads, we cannot bind a non-const lvalue reference of type to an rvalue. So, and this is maybe the point where where some of you already had contact with value categories in C++, because this is what you typically get when you get something wrong about value categories, and at this point typically you just stop caring about this and just then trying to fix it somehow, and then you're done. But this talk is really about to understand what is going on here. Why? What is the meaning of this error message? In fact, so. Let us talk about value categories. Or do you have any questions up to this point? Okay, this seems not to be the case. Let us talk about about the value categories in terms of Venn diagrams. So in C++ and also in various other programming languages, there are two types of values. There are values which have an identity, and basically these are values which you can access by typing in a variable name. So these things typically have names. And then there are objects which can be moved from, and what moving means we will discuss in the following. But we see that we do have these two categories, and they have an overlap. If something can be moved from, this is what we call an rvalue, and the thing that have an identity we are called global lvalues or GL values. And well, okay, then we have all the other sets. So something which has an identity but cannot be moved from, this is an L value, and the intersect are X values or expiring values. So let's look at a few examples. So let's start with this main function here. So in this main function, we initialize a variable a, and since it has a name, this is an L value, with the result of such a function. And as you can see, we don't name the thing this thing does not have a name. We just specify where do we get it from, but it does not have a name. So this is an R value, and to be more precise, this is actually a PR value, so a pure R value. So I put the Venn diagrams here, and you already see that PR values are really the objects that can be moved from, which do not have an identity. So don't get confused that this object does not actually has a name, because inside this function, of course, this has a name, but this doesn't matter at this point. At this point, we just specify how we create, how these things are created. And inside this function, the thing that we return is an L value. But at the point where we return it in line 9, this becomes a PR value. And then to say in line 12, we create another L value, which we name B, and we initialize it with A, but we do this to move A. And again, we will talk about this, but maybe you have already seen stuff like this in code bases. And this makes the L value A an X value. And this is something like we are now saying that A will expire. And what you should keep in mind is whenever you see something like this, you shouldn't use A afterwards. So in most of the times you will find that people say that if you move from a variable, the state of the variable is undefined. And this is also what I write here. It's nice to think about this this way, because then it's very easy to reason about, for example, this thing that this is an error. But unfortunately, this is not a runtime. This is not a compile time, or in most cases, not even a runtime error. But it's just in some sense undefined. We are accessing a variable or a member of an object which has expired. And we enforced we enforced this by doing the std move here. To be more precise, this is technically not correct, because it is not an undefined state. In this particular case, it's very well defined, and it's totally fine to access .x. but in fact, it's never undefined to access an object that has been moved from. But it really depends on the implementation detail of S. And this is something we should always consider the black box. So we should not care about how S internally handles such things. And so the consequence is that when you moved an object, consider this object as expired, and then you can reinitialize it with another, in this case with another S, and then it's totally fine to access X again. So std_move creates an expiring value. You enforce this, and afterwards you shouldn't access it. Okay, and there are questions going on. This is a compile time error. No, it's not a compile time error. It's in most cases, it's not even a runtime error, but it's you should consider it to be undefined behavior. So most of the time, accessing member variables will produce perfectly fine code, but it's most of the time not what you would expect. So this is definitely a code smell if you see something like this. I just wanted to be precise that in this special case, this technically works, but nevertheless, I should write code smell here. Okay. Yeah. Okay. So this is an X value, and now we can make our first attempt to understand what was going on before. So the message. The thing that we did was somehow similar to this snippet here. We had a function swap, which accepts references, lvalue references, and then did some stuff with it. And we passed in pointers. And an example T was a S star, but it doesn't matter. So it was some object or some type, and the address of an object. This is something you should never change. I mean, this is the position in raw memory, and actually the standard also is very explicit about this and says that memory addresses are always R values, because there's absolutely no reason in changing those. And what you're doing here, you bound something in R value which shouldn't be changed at all. And it's even strange to think about doing so to something where we say, okay, it's totally fine that you pass something here, and then you can change it, and this will also even have some kind of side effect. This is totally forbidden. There's an exception, and we will talk about this in the second part of this lecture. This could be a const reference. Then this is fine because there's some fancy lifetime extension going on, but we will focus on this a bit later. But the quintessence here is that you cannot refer to something that does not have a name and point, and memory addresses don't have names. They're pure R values. Okay, so let's now talk about std_move. This is an example where we use std_move. We have two functions. The one is taking a const reference, and the other one is taking an R value. So we have introduced this notation. Whenever we use two references like this, this indicates an R value, as I've stated on the right. So with basically, again, our two logging functions, which print A and prints B. And when we call f with just s, then this will print A, because this is then just a normal, this is just a reference. And this is where at some later point, maybe there will be a bit of confusion going on. So let me be clear about this. S at this point is an L value. And here it's also an L value, but the reference type changed. So here S is not a reference, but when we pass it to a function, then of course it is a reference. In this case, it's an L value reference. And by enforcing the type the value category of it to be an X value, then we can explicitly call the second overload, and then it will print B. See, there are questions. As ref is an R value or universal reference. We will talk about universal reference later. In this case, it is not a universal reference because S is not templated, but we will talk about this. Okay, so this is again a quiz question for you. What do we think? What is the output of this program? Let me launch it. It's very great for me to see that so many of you vote, because that's also great feedback for me to see how if I should go slower or slower or faster. So let me. Already 100 of you have voted. That's really great. So let me end it here and share the results. So you now should see it. Okay, so most of you think that it is ABAC, and stop the result. And well, see, it's ABAC. Okay, so let us shortly discuss this. So the A and the B shouldn't be such a big surprise. I mean, when the A comes from a line 11, and when we pass this to it's basically just invoking the copy constructor. So this is basically plain whole C++. So, but what is going on here? So we should expect to see an A, and so since this does not have a name, one could think that then the next result should be C, and then we would going on. But this doesn't fit with the result that we see. So what is actually going on here is that the standard is very explicit about this and says that this is a mandatory copy elision. It's interesting to see it's really mandatory. So even if you're going in on O0 in compilers, this this copy will be elided. So whenever you have this construct, when you initialize something with a PR value, the copy is skipped, which is great. But what you have to keep in mind. So this is the reason why we only see an A here. And then finally, the last line. Now we are enforcing the value category of S1 being X value, and that's the reason why we see C printed to the screen. I don't see further questions. Let's now let me go one slide back. What we did here, we looked which copy constructor is called. Now we are moving to functions. So we have 3 overloads. We have something that takes a const ref, a normal ref, and a ref, so an R value reference. So what will we see here? Well, of course, we see at first the A. We create this object. Then we pass this to F, and we see the 2 printed. Well, this is again should not surprise you. This is basically the thing that you would have expected even before this talk. Then here we again creating a new instance which does not have a name. So we see A, and then 3, and we see here there's no kind of copy elision going on. I mean, there's nothing we could save here. And then finally this last line, then okay, we are creating an R value, or to be more precise, an X value, and this will trigger again the third overload. Okay, so there's a question. Can you explain why there's an explicit copy? Slide 17. Which explicit copy do you mean? I suppose. No, could you explain on line 13? Okay. So there is none. There is no copy going on. So this is exactly what is happening. This is the mandatory copy elision. And you, if you have the slides, you can click on this. I put a link to it. So I hope I didn't confuse you. So there is no copy. The copy is elided. And you see this A because we create an object. Okay. So we understand this. So, and then this is again a quiz question for you. So again, what is the output of this program? Let me just launch it. So to explain the difference between these two examples, now the reference here is gone. So again, 100 of you have voted. So let me end it here and share the results. So you now should see the results. So and most of you think that it is A2A and 3.3. So let us see. Now it's a compile time error. And so let me stop the share. So it is a compile time error because of ambiguity, and to be more precise, in all three cases. So the first call, there's an ambiguity between the first and the second overload, because by just passing the object, there's no way to specify whether this should be taken by copy or by reference. The compiler cannot know which one of those we wanted to trigger. In the second case, there's an ambiguity between the second and the third one, because we could maybe we wanted just to create a new object for this function, which is taken by copy, or we want or technically we passed in an R value reference. So this could also be number 3. And the very same holds for the third example. Okay, there's a question. Can you explain why in the previous we have 33 in the end? So you were asking about these two 3s, I guess. This is because line 17 and line 18 are both invoking the same function. In this case, we create an object without a name. So this is a PR value. And here we are enforcing the value category of S1 being X value, which is also an R value. And so in those cases, we invoke the 3. How can I get 1 in output in this case? How can I so you mean on this slide? So Marco asked these questions. Yes, on this slide. So how to get a 1? You can't. That's a tricky part. I'm most certain. This could work if S is const. So then you would as written here you can't. But if S is const, then 1 is invoked. Okay. Okay. So okay, we had this example. So there are 2 more polls for this entire talk. So this is this is one, and then at some later stage there will be the last one. So let me ask you again, what is the output of this program now? So you see that I put back in the reference here, but now the main function has changed. Okay, so let me end the polling here. And share the results. I should see the results, and most of you think that the answer is 33AA. So let me stop it. And it's actually 23AA. Why is this? Well, an rvalue does not have a name. So let's look into this. So in this first place, we are creating an rvalue reference to this rvalue. So when we call this here, so we might expect to see a 3, but by calling this function, we use the name to something. We call this thing r1, so this is not an rvalue, even though here the type where the type seems to be this, but as long at the point where it has a name, it is not an rvalue. That's it. And if we really want to enforce the rvalue, we have to use std_move. Okay. Yeah. Cardo's happy now. Okay, so maybe we should now discuss what std_move actually does. So okay, so there's a question why 2a. Yeah, okay, this is also why. Sorry that I skipped this. This is why I added this print statement to the destructor, because you often hear that std_move kills in some sense the object that is passed by ending its lifetime. But this is actually not true, because in that case you would maybe does not see an A at all or see it earlier. But we see that the destructor are called at the very end of main. This is actually why I wanted why I had this slide. Std_move does not expire or kill an object. It actually std_move does not move, and std_move does not destroy, and actually does nothing at all during runtime. Std_move is nothing but a cast, an unconditionally cast to an rvalue. And you can, this is not the true implementation, but maybe you can think about it as this, where I already used some universal reference, which I will explain later, but you can just ignore this part. What we are doing here is whatever is passed as T, we get rid of all references. So if this is a ref, we remove it. If it is a ref, we remove it. And when there's no reference at all, well, then there's nothing to remove. And then we add two references to it. So in the end, R will be an rvalue. So the hint was in the name here. And then we simply cast T. And this is all that's going on. Std_move is nothing but an unconditional cast to an rvalue. So why is this important? Well, I've created this small benchmark here. and this is, of course, this is maybe the worst benchmark you have ever seen, but I think it conveys the message. We have two vectors of element size 1000, x and y, and then we start our benchmark looping, and then we just swap those. And this is the very same logic that we used at the beginning of this talk in our first implementation, and the first working implementation of swap. We swap x and y, and then we add some random elements together. And we do then we do the same, but now we move. So we create x by moving x into temp. Now x is, well, in some sense, in an undefined state, and as I already said, technically this is not right, but let's think about it that x is undefined. But we can reassign it with by moving y into x and then moving temp into y. And so, what do we guess? Which version will be faster? Well, of course, the move is much faster, and it is 900. It's 900 times faster. And this is, I mean, of course, this is a micro benchmark where we really focus on copying large structures. But this is something where this is something that you can expect from your program if you do a lot of unnecessary copies. You can get rid of these copies by clever usage of std_move. Okay, so I already mentioned it a couple of times, so let's talk about universal reference. What is universal reference? So by what you have seen so far, it is easy to assume that whenever you see two refs, then this is an rvalue reference. So let me ask the simple question. I have 6 cases here. And does ref in this case mean that this is an rvalue? And this is not a vote, but I just give you a few seconds to think about this. And you can also ask questions during this time. Okay, so in the first case, yes, this is an rvalue reference. So this is basically what you've seen before. When we use auto, then it is not. 3 again is a rvalue reference. This is basically the same that we have seen before. In case 4, it is again not. This, in the case of 5, this is technically a rvalue reference, but I would consider this most of the times a code smell, because it does not really make sense to have to enforce a move, but at the same time marking it constant. I have an extra slide coming where I will explain a bit about this. So, well, technically this is an rvalue reference, and 6 again is an rvalue reference. So that's the question: can you explain better 2 and 4? Yeah, sure. I mean, this is the entire idea of the section. So these 2 things are universal references. So let me first explain a bit more about this move and const thing, and then we will come back to this. So what I wanted to say with this slide is when you see such a program, so really these 2 lines, so you have a const s, and then you move it to an s2. You would expect this to trigger the move constructor, because you're very explicit about this. You just really enforce the move here. But anyhow, this program will trigger the normal copy constructor, and the result will be A. And the reason is that by stating that this, or by qualifying S to be const, this does not work with move, because with move we are saying that the implementation is free to assume that S is expiring and that it can easily move to some other place. So what actually has happened is implementation defined what what we define in S. But for example, consider this a vector. Then in the case of the vector, we would just simply swap the pointers to the underlying container. And this definitely does not work together with const. So this combination, having a const object and using std move, is I think always a code smell, and something that you shouldn't use. And this is very easy to get, and you can click on the Stack Overflow link for a nice discussion when you are passing objects to a function and accept these objects there as a normal lvalue reference, but then move the arguments to your internal members. Then you might think that moving it to the members will save a copy, but it will actually not if you take it by const reference. So this is just something I wanted to mention here. So, but then let us more talk about universal reference. Universal reference is actually, if I'm correctly, this is not the proper naming of it, but most of you will understand. Most C++ developers will understand what you're talking about. This term universal reference was introduced by Scott Myers in one of his great books. So what it basically says, whenever you have a construct like this, auto-ref or equivalently tref, where T is a template type, and these are the two examples that we had on the previous slides, then these are universal references. And if you find something like this, there's some kind of decay going on, because auto, or this case T, and this is auto is basically always the same, like template type, like a template type T. It's really just you can consider this syntactic sugar. These two cases are really equivalent. So auto or T can on their own already be a reference. So you can have stuff like this going on, like here, where you access an element from a vector, and when you use the brackets operator, then this will return a reference. So the type that is returned is sref. So auto will be sref. So in the end, you will have sref. And whenever you have these kinds of things, then there's some kind of decay going on. And so these are basically the rules that I used to think in, and there's one exception. So feel free to make up your own rules. So whenever you have, you always have to decay to at least at a maximum of 2 refs. So when we have 2 refs, it's fine. We stay with 2 refs. When we have 3 refs, we get rid of 2 of them. If we have 4 refs, we get again rid of 2 of them. So let's have a look at this example here. So the brackets operator return, or index, I think the proper name is index operator. So you see what I mean. Yeah. A reference is returned, and so this auto ref decays to sref. Here, this is an R value, so of type sref, and so the 4 refs decay to ref. Here we have S2 is a ref, so this will those 3 refs will decay to run ref. And finally, in the case of std move, this is the very same thing that we saw here. And there's one, well, I would not consider it a real exception, but the thing is, and this is also very important to keep in mind, and we will have a case where this is important later on in this talk, universal reference are always references. So the hint is really in the name. Universal reference are always references. So you might think that when we have something like this going on, we will end with an R value or so. But whenever you pass something on the right, which is an L value, then you should consider this to be a reference. So in this case, it also this will also decay to a sref. But I guess this is something that you would already have expected. Okay, so any questions to this point? Okay, so can you explain? Okay, S2 is ref, but as we call it, it becomes just ref. S2, let's have a look here. This part is an R value, so this is ref, and combined with these 2 refs, we will have 4 refs, which will decay to 2 refs. So in the end, this is what you expect. If you pass an R value, you will end up with an R valued reference. Okay. Can you explain next line, please? So you mean this line with a move? So so the question is auto ref S3. Yeah, okay, so this is this, no, S2, oh, so this line, you mean this line, okay. So here, S is a reference, and so this will decay, so these 3 refs will decay to 1 ref. So, you can think about it, this when we use it, this cannot be in R value because it has a name. And we will have cases. We'll have cases later on where we see this. At this point, at this point, it is really an R value reference. But as soon as we use it by name, it will become an L value reference. But I think I have examples for this later on. So let's just go to the next slides. And if your question remains, we can talk about this later. But maybe these next slides will help to understand. Okay, so there's one more question. Can you have 5 refs? I think this is not possible from a syntactical point of view, but I'm not sure. You could try it out, but I'm rather sure that there's no situation where auto could resolve in something like this. And that's the reason why I'm also quite sure if you try to type this by hand, then this would be a syntax error. Because these decayed rules are not the rules that are listed in the standard. The standard has really a couple of pages just to explain you how things decay. So this is a way for me to remember the rules, but you also have to keep in mind some exceptions. And you already saw that this example is a bit tricky because we here it is an R value, and then we suddenly have to name the thing, and then it's an L value. So this is very very hard to understand. I agree, but if you really want to have the full set of rules, you have to look into the standard, and I guarantee you that at least at the beginning you are even more confused. So let's go a bit further. I think this is already this is the last poll for you. So with everything that I've told you so far, what would you expect? What is the result of the output of this program? The trick about this one is it's basically, it all comes down, we will create at some point an instance of S here, because well, we are returning it. So at some point we have to create it, but the question is, what is the mechanism? I start with Paul here. And again, this time I really promise this is the last poll for today. It's also very interesting to see how many of you already have fell asleep. So at least 50 of you are still awake. That's great. Okay, so let me end this here. 90 of you have voted. Interesting to see. Let me share the results. So now you should see the results. So most of you think that it is ABC. Let me stop it. and the result is ABB. Why? Okay, so again, the A is again obvious. I think we don't have to talk about it. B should also be quite obvious, but why don't we see a C going on here? So what we see is the problem is that at some point we have to create this S, and obviously by doing this doing this cascade, we are losing the value category. So the question is how to do this in a proper way. How do we preserve the value category? Let me try, and this will also cover the question that you had before. Let us investigate this. So when we have a function that accepts an r-value an l-value reference and r-value reference, and then we print A and B, we could do the following. We create an r-value and then store this in our universal reference. And at this point, we can even do a static assert, and this program will compile where we assert that the type of R1 is really sref, so an R-value references. But if we call it, we will see A, and this is again the problem. We use it by name, and by using it by the name, then this is not an R-value anymore. So this is the same problem that we see previously, and we have to really enforce this by doing a static cast. So now we cast R1 to its type, to its very own type that we have asserted here, and then this will trigger B. And we can have the same here where auto-ref will decay to a normal L-value reference, and then we will of course see A. That this is should not surprise you. So we can also look at this from a different angle. I'm surprised that not so many people are aware of this, but you can also, you can specify that functions are const, for example, but you can also specify whether these are called in L values are when S is an L value or an R value. This you do this by doing the reference thing just behind the closing parentheses. Here we again create our R1 with an R value, and then call the function on it, and the output will again be A, which I agree is confusing. And the funny thing here is we can really do something funny like this. We can get the type of R1 and cast R1 to be this type. So this is really looks like nonsense. We are casting R1 to be its own type, and then we call F, and then the result will indeed be B. And the same is going on here. This is just to ensure that our assumption from the previous slide was correct. So on the previous example, we used the static cast here and typed in the hand the type manually, and basically we're doing now this the same here with the decay type. But it's I think it's very interesting to see that at that point when you use a name, even though the type is an R value, it will decay to an L value. This is really the idea behind R values. R values don't have names. And okay, here down here we're doing this with an L value reference, but the behavior is expected. So basically the question is how do we fuse two things if we want to preserve the value category? If in this example T is an L value, well, we want to trigger this implementation where we return an L value reference, and for the entire chain we want to keep it this way. But if it is an R value, then we want to return an R value reference, and we already see that as soon as we get something at hand, which is an R value, at each and every point we have to static cast it when we use it by name. to keep its category. And so we could, in this case, write static cast t ref, but this is in this case exactly equivalent to doing the std move, and this is maybe looking more familiar. And we could, so why we're just taking a ref here is because t on its own is already ref. So this is already the decay rule. And so the question is, how do we fuse this? Well, by doing this trick here. And here we accept the type where we again remove a reference and then just re-add it and then just cast it. And this is, you can think about it as the implementation of std forward. The actual implementation is a bit more involved, but it's maybe helpful to think about forward like this. And I know I'm already running quite late on time, so just let me say that if we use std forward in the previous example, then everything actually works as expected. So we are getting A, B, C, and the rule of thumb to keep in mind should be use std move when you have R values, when you know that you have an R value at hand, and use std forward for universal references. So universal reference means that you have a reference, but you don't know whether it is an L value and R value reference. So then you typically you want to preserve the category and then you use std forward. And well, this is we are now at a point where I hoped would be after half an hour. So maybe, yeah, okay. So just these two more slides, and then we will do the next we'll do the next thing where we continue here on doing the next slide. So just the question in this example, would you use std forward here for args? So what is going on here? We want to roll out our own very clever implementation for each, where we accept two iterators callable, and we want to call this callable operator for each and every element. And we assume that these operator does have some arguments. So basically, we loop through our iterators and then invoke this operator for each element. So whenever you see something like this, you will typically find in code bases that you do the universal reference here. The question is, why don't we use the universal reference here? And more specifically, why don't we forward here? So the problem is at the point where in cases where args are R values, you will steal the values with the first call. When you move them, you move the args to the very first invocation, and everything behind that could be considered undefined behavior. So this is something you really have to keep in mind. Never use an object that was moved from. And this is easy to say, but sometimes complicated to see when loops are involved. And so this is my last example, and every time that you give me, I will use to answer the questions, and otherwise we will continue here tomorrow. Thank you very much.
Okay, thank you very much, Nis. If there are some burning questions, I think we still have 1-2 minutes for questions if you want to write them or say them verbally.
Does it ever make sense to declare something as ref? So, and I assume that you mean that S is not a template type, so you really mean the reference. I've done it a couple of times. It's now difficult for me to come up with an example out of my head, but oh yes, there are examples, and we will see those in the next lecture when we use perfect backwarding. Okay, so Eric posted a code snippet with a vector. Oh, okay, there's an example. Yeah, but if this is meant as an answer to Jonas' question, oh no, it's not. Sorry, there's a question below. Are vectors element in undefined state? No, because so the example is that you use the typical for auto ref in a for each loop, because elements. You use elements in the block scope. So in the body of your in your for loop. So this is totally fine. But because the auto-ref just decays to a normal reference, depending on what elements returns. But this could be just a normal lvalue reference here. And even if it is an rvalue references, then then the iterator of S gave you back an R value, and this is really the indicator that S does not need this element anymore. Could be a very strange implementation, but technically totally fine. However, there are things where this is very dangerous when you are when lifetime extension is involved, and I have an example for this, which I wanted to cover today, but which I will hopefully cover tomorrow.
Okay, if there are no further questions at this point, then I propose to stop this lecture right here. So thank you very much, Nis, for this presenting this non-trivial those non-trivial concepts, and as always the lots of code and polls to make us think and challenge ourselves. Thank you very much. And as a reminder, there is the second part of this lecture about the value categories tomorrow at the same time, so 3:10. And now we have a couple of minutes of break, and we're restarting at 4:20 with the exercise consultation related to the big data technologies and distributed data processing with SQL, the lecture and exercises that Emil proposed and gave yesterday. So talk to you in a few minutes. So normally we will be starting in a few moments. Just to let you know, Emil is actually finishing another presentation at another online event. He will join us in just 2 minutes from now, as I was told. So please stay with us and we'll start very shortly.